Hello everybody. So today we are going to discuss the acidity and basicity of the compounds. So this is the most important area where you can get more number of questions in the entrance exams. So what are the basic concepts that are involved in determining this acidity and basicity? So when we take the oxides, here we are taking two types of oxides. One is the oxide in which the central atom is in +1 state, the oxide in which central atom is in +3 state. So now the central atom with +3 state, it is becoming more electron deficient. Due to more positive charge, it is more electron deficient. So to satisfy its electron deficiency, it will withdraw more electron density. When the central atom is in +3 oxidation state, so it becomes more electron deficient, and to satisfy that electron deficiency, it will withdraw more electron density from oxygen. So what happens due to this? The electron withdrawing tendency of cation or any atom, electron withdrawing tendency of any atom, we express in terms of electronegativity. But so here, as oxidation state is increasing, electronegativity increases. But for a cation, instead of electronegativity, we prefer to express in terms of polarizing power. So what is polarizing power of cation? It is Z²/R. So where Z stands for the charge of cation, or I can say that it is the oxidation state of cation. So as oxidation state increase, polarizing power of cation increases. That is, instead of using the word electronegativity, here we are using the word polarizing power. So when the oxidation state increases, polarizing power increases. And what is the effect of this polarizing power? When the polarizing power is more, the electron density of cation and the electron density of anion, they start overlapping with each other. When the polarizing power is more, electron densities of cation and electron densities of anion overlap. And due to this overlapping tendency, it is nothing but the covalent character of the bond. So what we mean to say is, when polarizing power increase, electron densities of cation and anion overlap with each other, and this is leading to the increase in covalent character of the bond. Covalent character of the bond will increase. So now, when the oxidation state increase, polarizing power increase, covalent character increase. And how can we correlate all these factors to acidity? That is, if you take this oxide in its aqueous solution, means we dissolve this oxide in its aqueous solution, forming the respective hydroxide. So when the polarizing power of cation is more, the electron density of oxygen is more polarized towards the cation. As a result, oxygen becomes electron deficient, and it will polarize the electron density of OH bond towards itself, leading to the increase in polarity of OH bond. When the polarizing power of cation increase, the polarity of OH bond increase, and that will facilitate the loss of H+ easily to the water, where the acidity increases. Means as oxidation state increase, metal oxygen bond becomes more covalent, OH bond becomes more polar, H+ liberation becomes easy, therefore acidity increase. So let us relate all these factors to acidity. That is, oxidation state, it is directly proportional to acidity. Electronegativity, directly proportional to acidity. Polarizing power of cation directly proportional to acidity. Covalent character of the bond directly proportional to acidity. Non-metallic character of an atom is directly proportional to acidity. So we can select any one of this factor and we can correlate it to acidity depending upon the examples given to you. Now when we come to the basicity, here I am taking the central atom, metal oxide, in which the central atom is in +1 oxidation state. So when the oxidation state is less, the polarizing power of cation decreases. Polarizing power of cation will be less, therefore the metal oxygen bond becomes more polar. The metal oxygen bond becomes more polar, therefore metal oxygen bond is more ionic. So simply to say, when the oxidation state of cation is more, covalent character is more, hence acidity will be more. And when the oxidation state of cation is less, ionic character is more, therefore it will increase the basicity. And how can we explain that? When we dissolve this oxide in water, it forms the respective hydroxide. And since the polarizing power of cation is less, metal oxygen bond is becoming more ionic, and therefore the bond is, it forms the respective hydroxide. Here metal oxygen bond is more polar or ionic, and this facilitates the loss of OH minus to water. OH minus to water, and therefore basicity increases. So when metal oxygen bond becomes more ionic, facilitating the loss of OH minus to water, leading to basicity. So here let us see the different factors, how they are correlated to basicity. That is, oxidation state of cation inversely proportional to basicity. Ionic character of the bond directly proportional to basicity. Electronegativity, it is inversely proportional to basicity. Polarizing power of cation inversely proportional to basicity. Metallic character directly proportional to basicity. So depending upon the examples given to you, you can take any factor and we can correlate it to the basicity. So now let us work out this concepts on the examples. Before that, what happens in the group and in the period? In a group, oxidation state is generally constant. Size of cation increase, polarizing power of cation decreases, metallic character increase, ionic character increase, basicity increases. That is, generally in the group, basicity increase. In a period, oxidation state increase, polarizing power of cation increases, electronegativity increase, covalent character increase, non-metallic character increase, so acidity increases. Simply, in a period, oxidation state increase, therefore acidity increases. Now, if you see the examples, here we are taking the oxide and hydroxide of first and second groups. So as you move from lithium oxide to cesium oxide, lithium hydroxide to cesium hydroxide, beryllium oxide to barium oxide, beryllium hydroxide to barium hydroxide. In all of them, the oxidation state is constant. Oxidation states are constant, and down the group, the metallic character increases. Metallic character is increasing, so ionic character increase, basicity increases. So in the group of oxides or hydroxides, basicity is increasing. Now when we take the period of oxides, so in the period of oxides or the hydroxides, what is the changing factor? Oxidation state. So when the oxidation state increase, covalent character of the bond increase, therefore acidity increases. Acidity will increase. Now, when we take the oxides formed by a single element, here I am taking the oxides of nitrogen. Again, the changing factor is oxidation state here. So when the oxidation state is increasing, the acidity increases. And that we can observe in the nature of oxides. So nitrous oxide, nitric oxide, these are neutral due to lower oxidation state, and the remaining nitrogen trioxide, tetroxide and nitrogen pentoxide. Here the oxidation states are high, therefore they are becoming acidic oxides. Similarly, if I take the oxides of chlorine, so here also the changing factor is the oxidation state of chlorine. So as the oxidation state increase, acidity is increasing. So oxidation state directly proportional to acidity. Similarly, I am taking the hydroxides, or I can call them as oxyacids. Hydroxides or oxyacids. Nitrous acid, nitric acid. Nitric acid has higher oxidation state of nitrogen, so more acidic. Sulfurous acid, sulfuric acid. Higher oxidation state of sulfur in sulfuric acid, therefore more acidic. And if I take the oxyacids of chlorine, hypochlorous, chlorous acid, chloric acid, perchloric acid. Oxidation state of chlorine is increasing, and that will increase the acidity. So this is the case of acidity and basicity in oxides and the hydroxides. But when we take the acidity in hydrides, so now the acidity in hydrides. Acidity in hydrides, it is decided by two factors. First one, electronegativity of central atom. So when the electronegativity of central atom increases, the bond polarity increases. So the tendency to release H plus in water increase. So we say that acidity increases. So electronegativity of central atom is directly proportional to acidity in the case of hydrides. And when you take size of central atom, when the size of central atom is more, the bond energy of HX bond or the bond energy decrease, so tendency to release H plus is increasing, acidity increases. Means due to the decrease in bond dissociation energy, the compound can lose H plus easily, therefore acidity increases. So in the case of hydrides, size is directly proportional to acidity. Now let us see those concepts in the compounds. So first, if I take ammonia, water, hydrogen fluoride, phosphine, hydrogen sulfide, hydrogen chloride. In them, the only changing factor is electronegativity of central atom. So as you move from nitrogen to fluorine, or as you move from phosphorus to chlorine, electronegativity of central atom is increasing, acidity increases. And if you take the size of central atom, so when you take hydrogen fluoride to hydrogen iodide, or water to hydrogen telluride, these are nothing but the group of hydrides. The group of hydrides, So in the group, size of central atom increase, bond energy decreases, so loss of H plus becomes more easy and the acidity will increase. So in the case of hydrides, size is directly proportional to acidity, electronegativity is directly proportional to acidity. Now, when we see the questions based on this acidity and basicity, so first I am taking the oxides. These are all the previous year questions I am discussing here. First one, you are asked with most of acidic oxide among the manganese oxides. So here the oxidation state is +1, +3, +7, +4. And we have already concluded that oxidation state is directly proportional to acidity. Therefore, the most acidic oxide is Mn2O7. Now, most covalent oxide. So, what is the factor? As the oxidation state increase, covalent character increases. So, if you are given with N2O3, N2O, N2O4, N2O5, oxidation states +3, +1, +4, +5. So, since oxidation state is directly proportional to covalent character, N2O5 becomes more covalent oxide. Now, most basic oxide. So, what is the relation between oxidation state and basicity? Oxidation state, it is inversely proportional to basicity. So, least oxidation state, more basic. So, here you are given with two oxides with +2 oxidation state, two oxides with +1 oxidation state. So, certainly the oxides with +1 oxidation state would be more basic. But among these two, how to identify which is more basic? That depends upon the metallic character. So, metallic character is more for cesium. In a group, always metallic character increase. So, cesium is more metallic, therefore, its oxide is more basic. Now, strongest oxy acid. You are given with the list of oxy acids here. And if you observe the oxidation states, so perchloric acid has the highest oxidation state of chlorine +7. Therefore, this is the strongest oxy acid. And if you see the order of oxy acids of phosphorus, so the oxy acids of phosphorus, hypophosphorus acid, phosphorus acid, phosphoric acid. Oxidation states +1, +3, +5. Means as you move from hypophosphorus to phosphoric acid, acidity should increase because the oxidation state is increasing. Acidity should increase, but it is decreasing. So this is one of the exceptional case. So how can you explain the reason for this? So in this, the entire acidity, it is decided by the non-bond, that is unprotonated oxygen. This we call it as unprotonated oxygen. Means which is not in the form of OH group. Unprotonated oxygen, and this unprotonated oxygen being the strong electron withdrawing group, it will initiate phosphorus to polarize the OH group so that hydrogen can come out as H+. So here in hypophosphorus acid, unprotonated oxygen, it has to polarize only one OH group. Here, two OH groups must be polarized. So here, three OH groups. So when the number of OH groups are increasing, the polarizing power of oxygen, the polarizing power of unprotonated oxygen experienced by OH groups is decreased, and therefore acidity decreases. So this is just because all of them are having only one unprotonated oxygen, which cannot polarize all the OH groups effectively. Therefore, acidity is decreased.